The next component of the test is the measurement settings. Here we actually set the settings for the measurement instrument. In case of EMI, we're going to go to option and make sure that the proper spectrum analyzer is selected. We use Rohde-Schwarz spectrum analyzer, and we connect it through the LAN Ethernet interface, which is quite fast, much faster than GPIB, for example. Let's test the connection. What we're doing right now, we're sending ID and question mark, and the spectrum analyzer replies properly. Okay, the connection is confirmed. So now we're going to measurement setup. There are two ways we can set up the test. It's a center frequency method and start and stop frequency method. Let's use start and stop. Let's say I want to measure the range from 100 MHz to 1 GHz. Let's set 100 kHz as a resolution bandwidth here. Number of sweep points. Now, number of sweeps is important. We're gonna measure the signal at max hold, which so we're gonna stay. This means we're gonna stay at the test locations for 2 sweeps and accumulate the measurements in max hold during 2 sweeps. We can also replace this by time. For example, if I click this, check this use time, it's gonna stay at a test point for 1 second. So I'm gonna set this to spectrum analyzer just to make sure all the settings are good. I can also save the settings to the setting library. Let's give it some name, and later I can load the settings and apply to my test, just like this. We're clicking OK, and the instrument is set. I'm also going to create a second test. As I said before, we're going to create a new scanning. We're going to give it a name. This is for scanning Y component, but I'm going to make a copy of the existing test. So this way I will inherit all the settings, even including the probe offset, which we set, remember? So the only thing I will change is the probe orientation. I will enter 90 degree. So this test will do exactly what the first one will do, except the probe will be oriented 90 degree, and will measure not X component of the field but Y component of the field. So all I need to do now, I have to run the test. I will select the components I want in the sequence I want and press OK to start scanning. The system moves the robot to start the position, and the probe starts. And now we get the first measurement. Now we will go through this again, but what you see actually in a plot, in a 2D plot below, is a kind of a max hold of all the points measured so far. For each frequency, it just looks through all the points scanned and plots maximum amplitude for each frequency. On a upper plot with a picture, you can see those colored dots accumulating, going from bottom to up. Those are the actual test locations, the locations the probe is landing right now. It's getting close to capacitor. I did not include that area, so it should turn and now go the other way. And point by point, it will create what we call the map. We're gonna switch in a surface mode probably soon. You see, right now it looks like the surface. So right now I'm swooping in frequency, and one more time, the bottom plot represents the maximum. For each frequency, it shows maximum amplitude for all the points measured so far, and the color map, each point of color map represents the maximum amplitude measured for all the frequency range at this point. So I'm sweeping in frequency and trying to find some hotspots, but it's frankly too early to see any activity. So point by point, real time, we see the map is updating, and slowly the bottom plot is also updating. If we find a peak, we're gonna see it immediately on the bottom plot. So this bottom plot, this maximum curve, is a really convenient way to understand what's going on the board just looking at one single plot. We can clearly say that, hey, for example, at this frequency, we definitely somewhere on that DUT we have very high rate of radiation, and on some frequency, if there is no peaks there, we can say at that frequency the board is quiet. So test is completed. Actually, both scannings are completed, and above you see the color map, and below you see the frequency plot. So right now I'm in a current slice mode, which means that on the bottom plot we still see the maximum frequency plot, maximum for all the points, and so we can change this mode to, let's say, a peak point mode, and in this peak point mode we're gonna see the signal that was measured in each individual point. But for now I'm just gonna sweep in frequency by moving this vertical red line on a 2D plot. We're gonna sweep in frequency and gonna see, and the top plot gonna reflect the color map for one single frequency, which is selected by this red line on a 2D plot. So I'm gonna select a peak point mode right now, peak point, and then whenever I peak, the bottom plot will display the signal that measured at that particular location. Basically, this signal is displayed on the spectrum analyzer when probe was at that location. This is a nice trace, noisy trace over here. I'm going back to the previous mode and sweeping in frequency. So as you see here, I'm at noise level, but we still see red color and blue color. That makes us think there are hotspots, but they're not. If you watch at the color scale, the minimum and maximum values are very close. To avoid this, we switch type to the absolute, which will use a minimum and maximum for the entire project. Then, as you see right now, noise appears like green blue color, and when we're coming close to a peak, yellow and red colors appear. So this is more like a true picture here. We can also set the custom range, which is very handy if we need to compare two different scanning. So we have to make sure the colors represent the same amplitudes. You can also watch that in 3D. Well, 3D is not only just the fancy looking feature. The difference in height, in elevation, helps our eye to distinguish between two different hotspots and define which one has higher amplitude, and also to understand what is the point on a PCB corresponding to that peak. We have this feature where we have a vertical line that links the points on the map to the points on the picture on the DUT. Now we're gonna combine those two scanning into a one to find the magnitude. So one scan represents X component and another one represents Y component. So we'll go to EMI menu and we choose merging data from the existing projects. So we'll give it good name, and then we open the existing project, and as you see, these tests can be located in two completely different workspaces, but in our case it's the same workspace. But the only requirement is that the number of points and the arrangement of the point is the same, which, well, it makes sense. We select which component is X component, it's already selected, and we click OK. What we see right now is the X component, basically our first test. So I can should actually go to magnitude, and now I see both tests combined. Let me go to surface mode. Let me add a little bit transparency so we can see through the map and see the PCB. And we start swooping in frequency and stopping at the peaks. Okay, we see some traces already, noisy traces. One of them was going to the memory chip. We see some traces coming from the oscillator. Makes sense. So this picture is a full picture. It combines both X and Y components. I'm just swooping through the frequency to... That was nice. Yeah. We see this on the right side with a trace coming from the oscillator, and the signal is coming out from the other side of the AC, going to memory chip. Probe has its own frequency response. So if we measure this DUT with two different probes, with two different sizes, we will get two different results. To make it probe independent, we need to account for that probe factor. That's why we need to apply probe factor to these results. We already have probe factor created, basically. So we go to EMI menu right now, choose apply probe factor. We go to our library, and I have probe factor for the probe, amplifier, and the cable I'm using right now. So all those losses and gains between the spectrum analyzer and the DUT will be taken into account. So I applied, I switched to calculate mode, and you see the curve changed a little bit, and you can also see that the units changed. We now dB milliamp per meter. So what we see right now is actually the field strength at the surface of the DUT, the actual field. Because it's H probe, we have amps. If we used E field probe, it would. Reporting is a really convenient feature to automatically create a Word report that will list the screenshots we think are important. So first we start with a template. So we just create a custom template like this, and then on the left side you see the window. This window will always stay on top. So this window contains some tags we're gonna input into our document. So this tag will identify the heading. So I'll just format it, give it formatting of the title, and the description of the test I'll give the formatting of subtitle, and then somewhere below I will include my screenshots with the descriptions. So those screenshots with the descriptions will be located between those two tags. So that's how I create a template in quite a flexible way. So here's going to be my image, and here's going to be the description of the image. And that's pretty much it. So we'll just close and save. The next step is to fill the data. So we go fill the data, we type in the title of my future report. I add description. And then I have to choose screenshot I want and the data I want. I can change the view angle, transparency, I can select the data I want and press plus sign to include that into my future report. Let me turn on interpolation so I smooth edges. Okay, so that's gonna be one of my screenshots. So I'm just gonna press OK, and so I started the list. Then I can sweep. Because of interpolation it's a little bit slow, I will turn it off. So I will sweep to a different peak, let's say this one, and we'll also include into the report. Now I can change the order if I want my recently added screenshot to be on the first place, So and so forth. I will add one more, but we can add many. This one, for example. Okay. Now I will close this window and I will generate the report in the template. So report is ready. This is my newly created Word document. So this is my title, this is my subtitle, and here go my screenshot with the description that reflects the frequency. That's it about EMI scanning technology, which is the easiest of all supported technologies, because it involves a relatively simple instrument and relatively simple setup.